is a pleasure to introduce myself, Sudip Kumar Acharyya, a retired professor of pure mathematics in the University of Calcutta. Today, the title of my talk is Discreetness of a space versus the von Neumann regularity of a ring. I must define and try to elaborate the technical terms involved in my title. With every topological space X, we can associate the set C x consisting of all real valued continuous functions on X, which makes a natural example of a commutative lattice ordered ring with identity. It turns out that there is a nice interaction existing between two apparently unconnected mathematical structures, one the topological structure of the original space X and the other the algebraic ring and order structure of the ring C x. For example, if X is a connected topological space, then one can readily check that the 0 and 1, which means the constant functions 0 and the constant function 1, these are the only two idempotents in the ring C x. What is remarkable is that this particular fact can characterize a connected space X, which means that if X is a topological space on which there are exactly two idempotents in the ring C x, then the obvious conclusion is that X is connected. Today, more specifically, I will focus on a particular type of problem in this area. It was established long time back in 1947 that if X is a discrete topological space, then every prime ideal in the ring C x of all real valued continuous functions on X happens to be maximal. In the technical term, we say that for a discrete space X, the ring C x is a von Neumann regular ring. What is remarkable is that the converse of this statement is valid if X is a metrizable topological space, which means that if X is a metrizable space for which the ring C x is assumed to be regular, then the conclusion is that X is discrete. However, if the metrizability condition on X is dropped, then the converse of such a beautiful statement might not hold good. There are some natural counter examples. So, I will first prove the basic theorem of Caplansky on which I have mentioned at the very beginning. So, let us start with a discrete topological space X. To prove Caplansky's theorem, we need certain technical notions. For example, if f is a continuous function on X, then the set of all zeros of the function is called the zero set of that function. A subset y of a topological space X is called a zero subset of X, provided it is the zero set of some specific continuous function on X. It is a standard result in the theory of rings of continuous functions that every zero subset is closed and also a G delta. In particular, therefore, if X is a discrete topological space, then such a zero subset is closed cum open, we call it is a Clopen subset of X. Now, there is a nice technique by which we can paste two continuous functions. Suppose A and B are two subsets of a topological space whose union is the whole of X, with the further property that A and B are both open or both closed. Now, if a function f defined on X real valued is such that its restriction on both of A and B are continuous, then it follows that the original function is continuous on the whole of X. There is another result which I need to use to prove the actual Caplansky's theorem. It is a standard result in abstract algebra that if R is a commutative ring with identity where the principal ideal generated by an element is identical to the principal ideal generated by the square of the element, then every prime ideal in such a ring happens to be maximal, which means that such a ring is von Neumann regular. And I can give a very simple proof, a sketch of the proof rather, to prove such a standard result. So, let P be a prime ideal of such a special ring R, where the principal ideal generated by A and A square are same, and A is an element outside P. To show that P is maximal, it is enough to check that the ideal generated by P and A is the whole of the ring. Indeed, if we take an element A outside P, then because of the hypothesis I can say that A equal to lambda A square for some lambda belonging to R. This implies that A multiplied by 1 minus lambda A equal to 0. Since A is outside P by our choice and P is prime, it follows that 1 minus lambda A is necessarily a member of P, and from this it follows that 1 can be expressed as the sum of two elements, one of which is a member of P and the other is a multiple of A. In other words, this yields that the ideal generated by P and the element A outside P is the whole of R. This means that P is forced to become a maximal ideal of R. So, this is a simple proof of the subsidiary fact which I will need to prove the original contemplated Caplansky's theorem. So, let us start beginning the proof of Caplansky's theorem. Here X is a discrete topological space, and suppose f is a continuous function on X. So, definitely as we have observed a few minutes back, the 0 set of f is a Clopen subset of X, and this information helps me to construct a function g defined on the whole of X by the formula that it takes the value 1 whenever f x is 0 and it takes the value 1 by f x whenever x is outside the 0 set of f. As because the 0 set of f is Clopen, we can make a simple application of the Pesting lemma to check that such a function g is continuous, and moreover it is not at all hard to verify that f is equal to f square times g. This means that the principal ideal generated by f and f square turns out to be identical. Hence, we can use a previous result to show that C x is a von Neumann regular ring, and that finishes the proof of Caplansky's theorem. Now, to prove the converse of Caplansky's theorem, we need to take care of some of the relevant facts associated to the structure of a metric space and some of the facts related to the ideals in the ring of continuous functions defined over such a metric space. Let me organize those facts one by one as far as possible. In a metric space, there is a special property that every closed set is also a 0 set. We can recall that in a topological space every 0 set is closed. So, metric spaces are specially gifted topological spaces on which one can never differentiate between a closed set and a 0 set. The proof is very simple, I skip the proof. Now, there is one particular property in a metric space which tells that if I consider a neighborhood u of a point A, then within that neighborhood I can interplace an open ball. More correctly, we can interplace a closed ball with a smaller radius. And since every closed set in a metric space is a 0 set, the whole thing can be organized to make this remark that in a metric space every neighborhood of a point contains a 0 set neighborhood of the same point. One more technical notion we shall use: with every point P in a metric space we can consider the set of those continuous functions on x which vanishes at the point P. We shall check and we designate such a set by the symbol MP. We shall check that MP is a maximal ideal in the ring Cx, and there is a particular subset of MP consisting of those functions which vanishes on a neighborhood of P. It is not at all hard to check that this second subset, which please allow me to call OP, it is just an ideal and it is a part of the maximal ideal MP. There is yet to prove that MP is a maximal ideal. So, I start. It is a fascination for me to give a formal proof of the fact that with every point P belonging to x, the ideal MP we have just introduced, it will turn out to be a maximal ideal. So, for that point P, we can define a function, let me call it psi, whose domain of definition is the whole ring of continuous function Cx, and whose range is the set of real numbers R, defined by psi f equal to f p. Please recall that P is already chosen, and one can readily check that this psi is a ring homomorphism onto R. That it is onto R is really important, and such a fact can be easily checked because of the presence of constant functions on Cx. And this homomorphism onto its kernel, the kernel of a homomorphism means the set of those points which are mapped to the element 0 in the range set. So, the kernel of this homomorphism is exactly the ideal MP I have introduced at the very beginning. If we use the first isomorphism theorem of abstract algebra, then from such a fact we can immediately make the remark that the residue class ring Cx modulo the ideal MP is isomorphic to the field R, as because a isomorphic copy of a field is also a field, it follows that the residue class ring Cx by MP is actually a field, hence the dividing ideal MP must be maximal. So, this is a simple proof of such a fact. Now, I shall prove a second fact that OP means the set of those continuous functions which vanishes on a neighborhood of P. This is a part of the maximal ideal MP. I shall check that MP is the only maximal ideal which contains OP. For that, it is enough to check that if I is an ideal which contains OP, then it is necessarily contained in MP. Because of the maximality, it will force that MP is the single maximal ideal which contains OP. So, let us start choosing a function f from I and a function g from OP, both arbitrarily. It follows that f square plus g square is a member of I, and therefore, the 0 set of f square plus g square must be non-empty, as because if I is an ideal, then for any function in that ideal its 0 set has to be non-empty, otherwise such a function turns out to be a multiplicative unit in the ring I, and if I is a proper ideal, it cannot allow any unit, because in that case it will turn out to be identical with the entire ring. So, f square plus g square is a member of I, and I is an ideal already chosen containing OP, it implies me that its 0 set is non-empty. So, this means that the 0 set of f intersected with 0 set of g, which happens to be the identical to the 0 set of f square plus g square, is also non-empty, and this can be further used to show that the 0 set of f meets 0 set of g. That means the 0 set of f meets every 0 set neighborhood of B. Please recall that we have already observed that every neighborhood of P contains a 0 set neighborhood of P. So, from this it follows that P belongs, every neighborhood of P must cut the 0 set of f. In other words, P must belong to the closure of the 0 set of f, but as because the 0 set of f is closed, this means that P should belong to the 0 set of f. In other words, f should vanish at the point P, which means that f is a member of MP, and this implies that the original ideal I, which was assumed to contain OP, is contained in MP, and therefore, MP is the only maximal ideal which contains OP. I require one more concept from the ring theory. In any commutative ring with identity, if I is an ideal, then there is a sister ideal, we call it the radical of the ideal I, which contains precisely those elements of the original ring, some power of which belongs to I. It can be checked that the radical of the ideal, we call it root I, is also an ideal and which contains the original ideal I. Some of the ideals are special, which are identical to the radical of their own ideal. They are called radical ideals. It is a standard result in the theory of rings of continuous functions that OP, I want to recall OP, OP means the ideal consisting of all the 0 set neighborhoods of a prescribed point P. It is a radical ideal of the ring of continuous functions Cx. There is a result, also a standard result in the ring theory, that if I is an ideal and root over I is the radical of the ideal, then such a radical is the intersection of all the prime ideals in R which contains the original ideal I. So, let X d be a metrizable space such that each prime ideal in the ring Cx is maximal, that is Cx is a von Neumann regular ring. We shall prove that X d is a discrete space, which means that every point of X is isolated. So, let us start choosing a point P in X. Please recall the ideal OP consisting of those functions which vanish on a neighborhood of P. We have observed that such a ideal is a radical ideal. Therefore, this OP is the intersection of all the prime ideals which contains itself. As because our original hypothesis tells us that it is a von Neumann regular ring, therefore, each prime ideal is maximal. Therefore, it follows that OP is actually the intersection of all the maximal ideals which contain it. But since MP is the only maximal ideals which contains OP, a result which we have established earlier, it follows that OP and MP become identical. This means that if a function, if a continuous function f on x vanishes at a point P, then it should vanish on a whole neighborhood of P. This is a very strong fact. Now, corresponding to the point P already chosen, let us define a function P which is nothing but the distance of a point x from the point P at an arbitrary point x. Now, corresponding to the point P which we have chosen at the very beginning of the proof of this theorem, let us define a function f whose value at a point x on x is simply the distance of x from that point P, and the distance functions is well known to be continuous. In fact, it is more than continuous, it is uniformly continuous, and such a function vanishes at the point P because the distance of a point from itself is 0 in any metric space, and this function vanishes at no other point. In other words, the function vanishes at the point P, but we have already observed a few steps back that whenever a function vanishes at a point, it should vanish on a whole neighborhood of that point. So, since this function vanishes at the point P and no other point, this means that the singleton P turns out to be a neighborhood of the point P itself. In other words, such a point P is isolated. As because the point P has been chosen at random, it follows that every point of x d is an isolated point. This means that x d is a discrete metric space, and that finishes the proof of the converse of Caplansky's theorem. Now, it is quite natural to ask whether the metrizability condition can be dropped for the proof of the converse of such a beautiful theorem. Answer is negative. We shall show by way of a counter example that if the metrizability condition is dropped, then the converse of Caplansky's theorem may be invalid. So, we start with a very, rather we should call a pathological example of a topological space. So, the underlying set of the topological space is an uncountable set with a special point, let me call P. The topology on X is defined as follows: every point other than that special point is an isolated point. So, this is almost a discrete space, but that special point P is never isolated. In fact, its open neighborhoods are huge. We declare a subset U of X containing that point P to be open, provided that set can afford to miss at most countably many points. In other words, open neighborhoods of P are co-countable subsets of X. Now, it can be checked that it is easy to see that this X is not a discrete topological space, as because the exceptional point P is not isolated. But it is not hard to check that every G delta subset of X is open. A G delta set means the countable intersection of open sets. Since every G delta subset of X is open, it follows that every 0 subset of X is open, as because we have recorded earlier that every 0 subset of a topological space is G delta. Therefore, since every 0 subset is open and every 0 subset is closed also, so it follows that every 0 subset is closed come open, and using this fact, if we recall our earlier example, it can be readily checked that starting from a continuous function f, we can achieve another continuous function g, which are connected by the formula that f equal to g times f square. This means that the principal ideal generated by the given function f, it happens to be identical to the principal ideal generated by the square of the function f. And if we recall an old result of classical algebra, this follows, this implies immediately that such a ring C x is von Neumann regular. So, we can organize our talk in that manner that we have started in the fag end of our talk with a topological space X, which is not a discrete one and which is also not a metrizable space, as because the exceptional point P, it is a closed set, but it is not a 0 set, because a 0 set is G delta, and we can readily check that such a special point one point X set P is never G delta, and in a metric topological space every closed set is a 0 set, every 0 set is closed. So, the singleton set P, it is a closed set without being a G delta, and that tells us immediately that such a topological space X is being far from metrizable, in spite of the fact just now we have realized that the ring of continuous functions over such a space is von Neumann regular. So, this shows categorically that if we drop the metrizability condition from the hypothesis of the converse of Caplansky's theorem, then the conclusion may fail. I believe that I should stop now. Thank you very much.